Welcome to Ask and Learn.
In this problem, we have a bar here, or a rod of some sort, that is resting against the smooth wall here, and then there's a cable attached to the end away from the wall, and up to a point above where it's touching the wall here. And so, in this problem, what we're asked, determine the height, which is kind of drawn poorly, but the height is the distance between where this cable attaches and this point here, or determine that distance h, to find out for this rod to be in equilibrium. So we have our force here, and we only have a force in the horizontal direction at this point because the wall is smooth and there's no friction, and then we're going to call that the origin. Now I'm going to call I'm going to say that this angle here between the negative x-axis and the direction of this cable, I'm going to call that phi. So this force has a magnitude F2, and then the direction is given by this unit vector. And then I'm going to call the angle between the negative horizontal axis and the rod theta. And that is, so then R2, the point, this point is given by the length of the rod here and this unit vector. Then we have a weight acting at the center of the rod because it's uniform in the vertical direction, or the negative vertical direction. And then this point here is half of this, so the direction is the same, the magnitude is L over 2 instead of L. So we have three forces and the positions of all those forces, and we can write our force and moment balances. And what we get out of that, we get an expression for F1 of x in terms of the weight and the angle phi, and we get an expression for F2 in terms of the weight and the angle phi, and then we also get a geometric constraint that says that cosine of theta must equal 2 times the cotangent of phi times the sine of theta. So that means that there's obviously, we had three equations here, and our other unknown is going to be this h value, and we can determine that h if we can figure out what these angles are. So we have this constraint, geometric constraint. So then I said, okay, here is the point, the position vector of C, which is the point where the cable attaches. And so if you go out to R2, that's the end of the rod, and then we know the cable had a length S, and so and then in this direction, so if you go out to the end of the right end of the rod and go back this far, you'll wind up at point C. And we know that the distance, or the position vector from point 1, or in the book, point A to C, should be just h in the vertical direction. And so that means that this vector should be equal to this. So that gives us some more geometric constraints that relate our angles here and our lengths to this distance that we're looking for, h. So then we also have this. And so the mess, and there's a couple pages of algebra I've left out of here because this problem is actually pretty ugly. And there may have been a simpler way of solving this. Maybe if I had used this angle here instead of this angle here. I'm not sure. But anyway, it's just a bunch of manipulating trig functions. And it turns out that you actually get a rather simple expression for h squared. And given the length here was 1 meter, and the length of the cable here was 1.5 meters, you get h equals square root of 5 over 5/12, which is, considering this ugly mess of functions here, is pretty surprising. And if you then, once you you basically have 3 equations and 3 unknowns here, and then you can get phi and theta, and it turns out phi is 59.4 degrees and theta is 40.2 degrees. Now, you could also say, well, there are actually some other very trivial solutions here. So if phi and theta are both 90 degrees, that means h is 1/2. So that means that the cable is straight down, and the rod is back up. So then this length is here. So basically everything's vertical. The rod is vertical, and the cable is attached in here. And so, h is 1/2, and these things are 90 degrees. Okay, so that's a trivial solution, and you can figure out that works out if we put that in here. And I think actually this should be minus, and this should be, let's see, theta was from here to here, so that's positive, and from there, so that's, that should be negative. Yep. And so if you plug this in, you can see that we have this winds up being sine of 90 degrees. Let's see here, sine of 90 degrees is sine of minus 90 degrees is -1. So we have h minus L. So h minus L equals s. So no, this was right. I had that before. It was positive there. So this should be a positive. That's right. I had it right. I was thinking I messed it up because I was looking ahead of my. And so we have h plus this thing is L is 1 equals S, which is 1.5 times 1. So we get h equals 1/2. And then the other solution, obviously, is if the cord is hanging straight down, and then the rod is hanging straight down from it. And so then we get h equals 5/2. So the whole distance, the length of the rod, the length of the cord plus the length of the rod. So those are actually 2 trivial solutions that technically are solutions. But I don't think they were the ones that they wanted you to calculate, because there's this kind of non-trivial solution where the bar is at this incline.